Hey Geometry Geniuses, I'm reporting live to you from my couch today. My phone's charging over there. This is my living room. Just thought I'd change up the video for today. Switch it up. This is where I live. Alright, now let's dive into 10.3. Dealing with area of polygons. In this lesson, we'll be taking a look at the area of different polygons. So not quite just squares or triangles or trapezoids, kites, rhombus scenarios. We'll be taking a look at more abstract ones. We'll be taking a look at the area of them, given its radius, side lengths, and apothem, which is a new vocab term. Not too tricky to get down. We'll also be using the special right triangles, which I have mentioned to you in the past, and also trig to take care of those. We'll take a look at the side angle side formula. I might cut off before then actually, and then take a look at further vocab for regular polygons. As we break this vocabulary apart for a regular polygon, you may want to pause the video, take note of this, copy this example, and then we'll touch base in a second. So pause the video, copy those down, and then we'll touch base. So what's this saying? The area of a regular polygon is related to the distance from the center to a side. So it makes sense. The center of this polygon is way in the middle, so we call that the center. No new vocab there. The radius can be measured from the center out to a vertex. And you might be curious as to why there's a circle going around this. So let's look at this bit here. This is saying that we can circumscribe a circle around any regular polygon. So we can have a circle map out around any polygon just like that. And it allows us to take it further and break it up into these other sections. The center of the polygon is the waist center of the circle. The radius is the distance from the center to a vertex. So notice we have several vertex points here. Since this is dealing with a hexagon, we have 6 of them. So in this case, we'll say that we have 6 vertices. The apothem is a new term, which measures the perpendicular distance. So notice that this line here in green is perpendicular to one of the sides of the polygon, creating this 90-degree angle, hence being perpendicular. And we'll eventually use that as we move forward. So really the only new vocab term that's here is apothem. And there's nothing too crazy there. For this figure at the right, for a regular pentagon, real quick, how many sides are on this? Hopefully you're saying 5. With radii and an apothem drawn, so notice that we have 5 versions of the radius sketched out. And we're being asked to take a look at the angles that are seen here. Pretty simple. So we can see that we have 5 angles divvied up around the center. So how many degrees is this full center going to add up to if we were to add up all 5 of those center angles? What do you think that would add up to? Hopefully you're saying 360. So in this case, let's take 360 divided by 5. So what's that going to be? Use your calculator for this if you need to. Got 360 divided by 5, so 72. So this is saying that angle 1 is going to be 72 degrees. Cool, easy. And then we start to focus specifically on this triangle that's here. So I'm personally going to redraw it. I know that the angle up here was 72. I know that the apothem is perpendicular, creating this 90-degree angle. And angle 3 was in the bottom right here. And angle 2 was up top here. Well, I know that if this is a perpendicular line that's cutting through, I know that this is going to bisect the 72. So I know that for this triangle here, What's half of 72? Hopefully you're saying 36. So in this case, we're allowed to say that angle 2 is 36. Because again, this apothem bisects that top angle. And then how can we go about getting angle 3? Well, we know that given this right triangle, this should add up to 180. So if we take 180, we get rid of 90, we get rid of 36, this should be equal to 54. Pretty simple to get a hold of those angles. We can do the same thing for a regular octagon. Maybe pause the video, try this one out. Well, I know that for one of these triangles, I know that if I took 360 and divided it by the number of sides, so 360 dividing that by 8, that'd be 45 degrees. So that would be for angle 1. And for angle 2, again, redrawing this apothem bisects 45 degrees. So this is going to be 45 over 2. So what's that, 22.5? And what does that leave angle 3? Hopefully you're saying definitely the leftover 45, so you want to keep the 45. But you also want to add up the difference. So the 22.5. So this gets you 67.5 degrees for angle 3, which was down here. Boom. Not too bad. So notice we haven't even found the areas yet. But as we move forward, we can divide up these triangles if we want to get a hold of the area that we're looking for. So in this case, an equilateral triangle, where all of these sides are congruent, has side lengths of 10. Find the area of the triangle, leave your answer as an exact value. Well, I know that normally we do 1/2 base times height to get our area, but do we have our height of this? Do we have that? Not quite. So let's divvy this up. We can break this down. We know that this is 10. That would make this 5 and 5. If this is an equilateral triangle, what do you think these angles are going to be? Hopefully you're saying 60. And that would make this 30. This 30. So what does that make this apothem? Let's break this apart. So we know that this top angle here is 30. We know this is 60. We know this is our right angle. We know this is 5 because it's half of this 10. And we know that our hypotenuse is 10. Recall from special right triangles that across from 60 degrees is our smallest side times √3. So boom, we've got our height now. So now if we take this back, going for our area, this is going to be 1/2 times our base of 10 times our height of 5√3. Getting us half of 10, which is 5, times 5√3. So this would be an area of 25√3 meters squared. So notice that I had to draw this out, I had to divvy this up, I had to redraw this new triangle, and then I had to recall special right triangles, which is okay. If you get stuck on those, let me know. What else do we got? This allows us to then take this further with the actual area of a polygon. You can pause this and read the postulate if you want, but I'm just going to dive right into the formula, where if we're aiming for the area of a regular polygon, this is half the product of the apothem and the perimeter, which makes sense because if we were going to divvy this up, our perimeter Like, think of this as if we just cut this apart into 6 different triangles. You would have 1, 2, 3, 4, 5, 6, where the total perimeter is your base and your apothem acts as your height. So you really have all of these triangles. So it makes sense that it would be 1/2 times your base of P times your height of A. So that's an interesting way to think about it. We'll do a few of these examples. Regular decagon, so 10 sides, has a perimeter of 40 feet and an apothem length of 5. I'm not going to draw this out. I'm really just curious about what this area is going to be. So I have 1/2. Apothem is 5. Perimeter is 40. So this is going to give us 100 feet being squared. Simple enough. What's the area of a pentagon? So now with how many sides? 5. This I'll do a quick sketch of. We have an apothem of 8 centimeters, and our sides are 11.6 for all 5. So if we take this further, it's as if we have how many versions of this 11.6? Well, we know that we have 5 sides, 5 versions of 11.6. So this is going to be our perimeter. So what would this be? 58? 58 centimeters for our perimeter. And then if we're going for our final area, this is 1/2 our apothem, which is 8, times our perimeter, which is 58. So this is going to be 4 times 58, which is 232 centimeters squared. Simple enough. Again, not quite drawn to size, but I think this section's pretty easy. I may post another video to talk about the next few examples, but I hope this was helpful. Notice that we started just divvying up the triangles that are seen inside of these polygons. But now we can use, in addition, this area of a regular polygon equation. I like both of these ways. I like how we have to kind of divvy up the polygon to make sense of it, but the equation's also nice too. I hope this was helpful.